Institute of Physics. Okay. And later on, he moved to various places, various great places. He's working on the field of dynamics in galaxies, and we hope to have a very nice talk in our meeting. So, Eugene.
Thank you. Yes, I'm really happy to be introducing this year's whatever seminar series. And unfortunately, not there in person. I was in Athens actually last year for a Gaia meeting, and gave a talk that was quite not unlike this one, but today I'm going to give some updates. So the subject of this talk will be on the interaction between our galaxy and its nearest neighbor, and largest, well, not nearest, the largest neighbor, the Large Magellanic Cloud. And as an introductory picture here is the standard setup in the all talks about galactic astronomy. That's the image of the sky as seen by the Gaia satellite, because that's actually to a large extent what drives the Milky Way science in the last few years. And LMC is this blob here down in the southern hemisphere. And well, that causes a lot of trouble. So what kind of trouble we are talking about? Let me first introduce the two galaxies. As we know them, the Milky Way is a pretty average spiral galaxy. In fact, I think many galaxies are measured with relative to the Milky Way. It's kind of defined as a standard galaxy, much like Sun is defined as the standard star. The stellar mass of the Milky Way is a few times 10 to 10 solar masses. The total mass is about 10 to 12, and so on and so forth. LMC, by all measures, is considerably smaller by a factor of between 5 and 10 in stellar mass and size and everything else. But they are both kind of regular, or maybe not quite regular in the case of LMC, but quite typical spiral galaxies or disk galaxies. And as for the relative orientation of the Milky Way and LMC, as I will talk about in more detail, the LMC is currently experiencing its pericenter passage around the Milky Way. It just passed the pericenter passage some short time ago, maybe about 100 to 100 mega years, and probably for the first time. So from this comparison, it's clear that Milky Way is a big guy and LMC is the smaller one. So why does it cause so much trouble? The trouble comes from, trouble and of course opportunities come from the way that the two galaxies interact. The LMC is small, but it's not negligibly small. And so here are the topics that I'm going to cover in this presentation. And starting from kind of good things, that LMC brings some stuff in our Milky Way system. And that's something that I'm going to talk about towards the end. But all the rest are bad things. So it deflects stars and the stellar streams that are in its vicinity, hindering their interpretation. It creates some sort of perturbation in the galaxy and displaces the entire Milky Way, creating some sort of asymmetries and affects basically our motion with respect to the rest of the universe. So let's see how it goes. Let me start with the stellar streams. And for those of you who might not have heard much about stellar streams, these are structures that you get from tidal disruption of star clusters or satellite galaxies in the gravitational potential of the host galaxy. And here is an example of kind of the model of a stellar stream. If you take a small star cluster and place it on an orbit, it of course suffers from sort of tidal field. And the material that is lost from the two Lagrange points creates leading and trailing arms of the stellar stream. And as these cluster orbits for a long time, the stream that it creates gets longer and longer. And of course, the mass of the progenitor system gradually decreases until it disappears entirely. And these streams have been studied already, observationally studied for a good 20 years, starting from 2MASS and SDSS surveys back in the early 2000s, and then more recently with Gaia. Here is an example of an iconic picture, which even has its own Wikipedia page called Field of Streams, where you see the largest of them, the Sagittarius stream. Again, I'm going to talk about it more shortly. But there are also other things crisscrossing this patch of the sky. And more recently, with the Gaia data and also other spectroscopic and photometric surveys, we get much cleaner views of these stellar streams. Here is the stream from the Palomar 5 globular cluster, one of the best known ones and very clean ones. The difference that we could immediately spot is that this stream is much thicker than this one. And that's because the progenitors are different. In this case, it's a big satellite galaxy. In this case, it's a small globular cluster. So not naturally, the stream from a small object will also be thinner and colder kinematically. And now by 2023, the streams in the Milky Way have been, not all of them probably have been discovered, but we already have about 100 or so, which are here shown in the compilation of the Gauss Streams database. We even have that thing in astronomy, database for streams, all the wanted subjects and so on. And so what happens with the streams if you have more than just the host galaxy and the progenitor of the stream? If there is a third body coming in, as you could imagine, a passing by object could deflect the stream in various ways. And that's exactly what happens for some of the stellar streams. One of them that was historically the first one to demonstrate this kind of deflection is called orphan Chenab. Orphan stands for the fact that we don't have any progenitor for the stream, so it seems like an isolated stretch of stars. So progenitor has probably disappeared already. Chenab is the other stream that was discovered independently, but since then it has been linked to orphan, and now it looks like there is a continuous stream both in the northern and the southern hemisphere of the galaxy. So the missing link was across the galactic plane. So it spans more than 280 degrees in the sky, so a very long one, also spanning a lot of a large range of galactocentric radii. And what is interesting about this stream is that, of course, a stream is defined by its position on the sky as a stream of stars. But also, thanks to Gaia and spectroscopic surveys, we are able to measure the velocities of stars in the stream. And the interesting thing about this stream is that the velocity is actually not aligned with the stream track. And that is something that you could expect to be happening naturally. And stars leave the progenitor, they still travel along more or less the same orbit. So if there is a misalignment in velocities, that means that something must have deflected the stars in the stream. And we suspect, with good reasons, that this is the Large Magellanic Cloud, because in fact, it's only 25, 30 degrees from the stream itself. And it passed closer to the stream some time ago. So instead of being on a relatively straight line, the stream actually gets this kind of weird kink shape, and not only on the sky, but also in the velocity space. So this has been seen as the indication that, yes, the LMC deflects stellar streams. So of course, making interpretation of the stream and detection of the stream more difficult. But also, not only this stream, but over time, several other streams in the southern hemisphere have been analyzed, and they also display some sort of features in the kinematics that are misaligned with the stream track. So seeing an indication of LMC's perturbation. And if you think about it, the larger is the mass of the LMC, the larger is the perturbation. So you could not only complain about this unfortunate circumstance, but also turn it to your profit and use it as a tool to measure the mass of the LMC. And that's what has been done by these people here. There are several groups who are doing this analysis. And it's not a single number that you get from this exercise, but because stars at different positions along the stream experience different type of perturbation, you could actually try to measure the mass profile of the LMC. And also because different streams also stay at different distances of closest approach from the LMC. So all in all, you kind of try to map out the mass of the LMC as a function of radius. Even from the orphan Chenab stream alone, there is quite strong constraints on the mass profile, getting to better than 20% precision at the closest approach point. But other streams also have been used for the same purpose. And there is a general consensus that in order to produce the observed perturbations of these streams, the LMC has to be pretty massive. And by that, I mean it's between 1 and 2 times 10 to 11 solar masses, or 5 to 10 times smaller than the Milky Way. And that revelation actually was not, I wouldn't say unexpected, but it was something that we have to contend with, because historically there were many studies that considered LMC to be much smaller, but now from the dynamical perturbations on the streams, we see that it actually has to be pretty large or pretty massive. The stream that is the most prominent feature on the sky is the Sagittarius stream that has been discovered more than 20 years ago. And it's produced by the Sagittarius galaxy, which itself is the third largest satellite of the Milky Way after the two Magellanic Clouds. And unlike the two Magellanic Clouds, it seems to be orbiting the Milky Way in much closer proximity for quite some time. And that's why it has actually produced a lot of stars emanating from both ends. And here is the picture. There are overlaid the stars from the Gaia catalog, which are classified as part of Sagittarius. The Sagittarius galaxy core is sitting right here below the galactic disk, and it's still relatively close at galactic latitude of only -15 degrees. And its past orbit was looking like this. It actually stays on a relatively polar orbit. So it goes through the disk, and the trailing arm is in the southern hemisphere. The northern hemisphere keeps the leading arm. And the LMC on the same picture traverses more or less in perpendicular direction. So it crosses the path of the Sagittarius stream, but as we will see, its deflection on the Sagittarius stream is actually more complicated. Its effect is more complicated than just a simple deflection. What do we know about the Sagittarius stream? Quite a lot. As I said, it has been mapped out across the whole galaxy, and both in photometry, in line of sight velocities, and in the proper motions. So we have a full 6-dimensional picture of the Sagittarius stream spanning more than 360 degrees on the sky. And here are some projections of this data. If you measure the position along the stream by lambda, the latitude along the stream, with 0 being pointing towards the remnant, the Sagittarius galaxy, and the positive values of lambda going for the leading arm, negative going for the trailing arm. These panels here show the profiles of two components of proper motion, right ascension declination, distance, and the line of sight velocities. And this panel here is showing a similar feature to the orphan stream, namely that the velocity vectors of stars in the Sagittarius stream are pointing at some angle with respect to the stream track itself. Or the lower panel here is the same thing expressed as the misalignment between the gradient of the stream track, the dashed line. No, sorry, the stream track is the red line, and the dashed line is the gradient of velocity. So there is a mismatch. These vectors do not point along the gradient of the stream track. And this kind of misalignment cannot be created by any static potential. So you have to make some sort of time-dependent perturbation in order for this to work. And to illustrate it, here I'm showing an example of a model for the Sagittarius stream forming in an embodied simulation, tailored to reproduce the properties of the remnant galaxy and the stream. So it's kind of galaxy collision, but tailored to a very specific situation here. And in doing this exercise, that's what I've done a couple of years ago, I had a lot of flexibility in how I choose the Milky Way potential, trying to optimize the parameters of the potential in order to best reproduce the properties of the stream. But if I compare the data with the model, there are two places where they don't match up. The first one is the mismatch between the upper center of the leading arm. In the data, it is closer to the sun than in the models. Even if I try to adjust the potential to match it, I wasn't able to make a perfect fit. And the second is that there is no misalignment between the stream track and the proper motions. So that misalignment, as I said, could not be created in any static potential. So in order to make this work, I had to introduce the LMC's passage as the perturber. And if I do so, I happen to fix both deficiencies, and the comparison between the data and the model is now much better. So Sagittarius stream is yet another example where the LMC has introduced some sort of perturbation. But interestingly enough, most of the perturbation here, you see it in the leading arm, which is shown by yellow colors here. Whereas the LMC, of course, sits in the southern hemisphere. So it was actually passing closer to the trailing arm. Why most of the perturbation comes in the leading arm? Because the action of the LMC is more complicated than just the direct deflection of stars in its vicinity. And that comes back to the question that I already announced, that it creates a global perturbation in the entire galaxy. But before we go there, let me keep on with the local sort of perturbations. And here is another effect that is relevant for any kind of moving body, be it a galaxy like LMC or a globular cluster or anything else, like an isolated black hole. A massive body moving through a sea of background stars creates what we call a density wave. And that's coming because stars, when it moves through this sea of stars, the stars get gravitationally deflected, and they form some sort of overdensity behind the orbit of the motion of the massive body. And of course, this overdensity now creates a gravitational pull, and that leads to the deceleration of this moving massive body, which is a Chandrasekhar dynamic of friction in a nutshell. If this moving body is a big, chunky satellite galaxy like the LMC, the perturbation that it creates will also be quite large. And it's not only in the, well, it is the perturbation in all kinds of objects, stars or dark matter particles. And stars, if they're deflected and form the trailing wave behind the LMC, that should be seen as an overdensity if you look at the sky. And that's what has been tentatively detected by a couple of groups as the so-called Pisces overdensity. Pisces is the location on the sky a few tens of degrees across the LMC. So it's a trailing wave, and there seems to be an overdensity of RL-Iris stars at large distances in the halo. So fine, that could be expected. And so this overdensity is something that naturally comes up with any kind of discussion of dynamical friction of a moving body. But what is less, what was probably less obvious until a few years ago, is that this is not the only effect of the moving body. So let me now show you an illustration of the Milky Way and the LMC colliding. And I'm showing the contours of course, it's a simulation tailored to, again, to a specific case of these two galaxies. And I'm showing the contours of the density of both galaxies and the velocities of the Milky Way stars only. And as it goes, so the LMC passes, and that's roughly where it ends up now, some 50 kiloparsec from the galactic center. As it goes, what happens first, if you look at stars in the vicinity of the LMC, the velocity vectors get deflected and they create an overdensity. That is the classical Chandrasekhar dynamic of friction. You can see that there is kind of a bulging overdensity. Contours get bulged towards the past trajectory of the LMC. That is the standard Chandrasekhar dynamic of friction wave. If you look at the entire rest of the galaxy, you notice that the velocities of stars are not the same, because stars that are further away from the LMC, they don't get as much gravitational pull, so they get accelerated to a smaller extent. And since the most of the interaction was occurring very recently, as I said, it's about 100 million years ago, the inner part of the galaxy got mostly accelerated and got the velocity directed downwards, whereas these guys over there, they haven't really got that much of downward impulse. They still keep going sideways. So now the velocity of stars across the galaxy has some sort of spatial dependence, or in simpler terms, that means that the galaxy gets deformed, because these stars have been moving downwards and they have been displaced downwards, whereas these guys have been not displaced downwards that much. Now, the sun is at about 8 kiloparsecs from the galactic center, so it's roughly here. And all this region here, they gets roughly the same acceleration, get the same displacement, same velocity. With the sun, we are sitting in the reference frame associated with the galactic center, and that's where we used to do all our analysis in this reference frame. But this reference frame itself is moving. So if you now transform to this reference frame, sorry, this picture is the same, but it's now the axes are flipped. Sorry for this mental adjustment. The velocity vectors of the inner galaxy are mostly directed downwards. If you now transform to the reference frame where the inner part of the Milky Way is static, we see that we have to subtract this velocity, and we see that the rest of the galaxy at larger distances is kind of moving upward. And that's because it was not moving downwards sufficiently to catch up with the inner galaxy. So it's, in other words, this is a reflex motion imparted by the moving LMC onto the inner part of the galaxy, and not the same amount of reflex motion has been imparted on the outer part of the galaxy. So this is the physical mechanism for what we call this global perturbation, and the most dramatic effect is creating this dipole polarization pattern, where the stars in the outer galaxy have not moved downwards as much as the inner part. So by now, they find themselves at larger distances than from the galaxy center than they used to be, if you look in the upper northern hemisphere. And conversely, in the southern hemisphere, they are suddenly pulling closer to the galactic center. So that is to say that the density contours now get deformed, and it gets over density of stars in the opposite direction from the LMC and under density in the direction of the LMC. And that is in addition to this local over density coming from the dynamical friction wave. So if you were to separate these two factors, this transient wake or dynamical friction induced wake is the localized over density of stars. And then there is a global response where in the opposite side from the LMC, there is an over density of halo stars, and in the direction towards the LMC in the southern hemisphere, we have under density. And this has been analysis has been carried out by a few groups using both embodied simulations or some sort of perturbation theory that they all point towards this effect to be important. That's something that is actually overlooked by the classical Schneider-Secker dynamic friction theory, because in that theory, you only look at the local perturbations. You assume that the galaxy is fixed. Of course, the galaxy is not nailed down in space. It moves and deforms differently, function of radius. So just to summarize, this deformation of the galaxy is probably the most interesting and important effect of the LMC, and its importance only became apparent in the last few years. Theoretical models and body simulations predict that the most dramatic signature you would see in the density and in the velocity. So here is the picture showing the density or over density contours. Yellow would be higher density, and blue is the lower density compared to the mean expected density. And at the path trajectory of the LMC, you would have an over density corresponding to the dynamic friction wave, and then this global dipolar pattern where northern hemisphere will have over density, southern hemisphere will have under density. And the same thing should be seen in the line of sight velocities, because again, things in the north are receding from you, and things in the south are approaching to you. And these are predictions. And on the right, I'm showing the observations. So both the density of distant halo stars seem to display a pattern that looks qualitatively similar to the predictions. You have LMC sitting here. Its path trajectory goes like this. There is a density wake on its path trajectory, and then there is also over density in the north, which is interpreted as this dipolar pattern. And the velocities of distant halo stars and other objects like galactic satellites, if you plot the z component of velocity in the galactic-centric reference frame, z component is kind of moving upward, and there is a net motion upward in the outer galactic halo. So both things match qualitatively and even quantitatively to some extent the amount of perturbation expected for the LMC of the mass between 1 and 2 times 10 to 11 solar masses, again, going back to the same mass range. So I have some sort of consistent picture here. But importantly, these over densities and perturbations really become apparent only at larger distances, roughly halfway between the galactic center and the LMC. That's where you start to see these deformation patterns in the galaxy. Given these kind of perturbations, what does it do to us, like dynamical astronomers? One of the main things that one of the main questions that we could ask about a galaxy in general is, what is the mass distribution? And what is it made of course? Count the stars, you count the gas, you ascribe to dark matter. There are many ways of doing this dynamical modeling or inference about the mass potential, the mass distribution and the gravitational potential. Broadly speaking, you could break them down into 2 big classes, at least 2. One is based on stellar streams. And the idea here is that stars that left the progenitor, they move roughly on the same orbit. So if you try to map it out on the sky and then try to fit an orbit, the orbit, of course, depends on the potential. So by fitting an orbit that passes through the observed stars, you should be able to provide constraints on the gravitational potential. And the other class of methods, there are many different methods here, they deal not with strings, but rather with smooth stellar populations, like galactic halo stars, for example, or the population of globular clusters in the galaxy, or even galactic satellites. And the idea here is that these populations are assumed to be in dynamical equilibrium. So even though stars on average move, but the overall shape and the distribution of velocities is assumed to be quasi-stationary. And in order for it to stay stationary, the galaxy must have a particular mass distribution. So again, if you measure the positions and velocities of many objects and try to match them by varying the gravitational potential of the galaxy, you should be able to find the best fit and therefore infer the potential of the galaxy. Now, both methods obviously will be thwarted by the presence of the LMC's induced perturbations. And a while ago, a paper led by Daniel Circle, the same guy who was studying the orphan stream, they concluded that these kind of perturbations, in the context of Jeans modeling, at least, they would lead to an upward bias of the inferred galactic mass. And probably the most intuitive way of thinking about it is that since the LMC induces the motion of the galaxy halo at the large scales, with the velocities of a few tenths of kilometer per second, if you compare it to the mean velocity dispersion, which is about 100, that's not a negligible amount. That's probably, yeah, a few tenths of percent. So all in all, the velocities of objects in the outer galaxy are higher. And if you try to match them up with the equilibrium model, you'll have to put more mass there. So that will bias the inferred mass upward. And now the question is, we have a well-developed methods. So all of these items here have a long history of development by various researchers, and we are kind of going from very simple models to rather sophisticated models. And I try to picture it here as a progression between several pieces of classical art tailored to a specific audience. And they are going from very simple models to rather sophisticated models like these ones, like made to measure in orbit superposition method, are quite sophisticated. But should we just throw them into the bin, given that we have such enormous perturbations recently? Or is there a way to adapt them to kind of being modern while still retaining their classical heritage? And my take on that was that I'll try to salvage them and adapt them to this dynamic context, the context where you cannot assume equilibrium, but you still can invoke methods based on equilibrium assumption. And here's how I would do it. So that was a summer project Lilia Correa-Magnus was doing with me a couple of years ago. The idea here is that the LMC moves around the Milky Way in a predictable way. If you assume a mass distribution for the galaxy and assume a mass for the LMC, you can compute how the trajectory looked like in the past. And therefore, you could also try to compute how the trajectories of all your dynamical tracers, how they were perturbed by this moving LMC. And if you now turn the time backward, you could try to backtrack the trajectories from the present day state, which is perturbed, back in time to the supposedly unperturbed state. So the assumption here being that before the LMC came in, the galaxy was generally speaking equilibrium, so all these methods would apply. And the only thing that we need to do is to undo the perturbation caused by the LMC in the last giga-year or so. And you'll have to do it for every choice of the Milky Way potential and every choice of the LMC mass. And then after this rewinding step, undoing the perturbation has been done, then the classical modeling methods would apply, which are based on equilibrium assumption. And they hopefully could inform you whether your chosen potential was a good one or you need to adapt the parameters. And so this loop will have to be done many, many times, and finding the gravitational potential that matches the present-day perturbation, including the present-day distribution of objects, including the perturbation by the LMC. And in this context, we used two different tracer populations. One is the set of globular clusters in the galaxy, which are about 150. The other is the set of galactic satellites, which are much less numerous, but they're also spaced out much more. And again, with the Gaia data, we now have full 6-dimensional phase space coordinates for most of these objects, measured very accurately. So here is the summary of findings from this experiment, which is shown in red, and many other studies. This panel here is just a compilation of studies done in the last 5 years, roughly, since the Gaia data release 2, which really revolutionized our understanding of the dynamics of the galaxy. Most of these methods did not take into account the LMC. The 3 highlighted ones are the ones that do take into account. The red one is just based on what I described, the equilibrium models applied equilibrium models, assuming that the LMC moves on a predictable trajectory and taking into account the perturbation from the LMC. And the blue and the green contours show the enclosed mass profiles inferred from the study of 2 streams, the orphan stream and the Sagittarius stream. And as you could see, they actually match up very well and surprisingly well. The third one, which is based on the kinematics of satellites and galactic global clusters, is a bit higher, but is compatible with the uncertainties. And as I said earlier, the perturbation of the LMC, if you ignore it, it will bias the results upward. And that's probably what I have seen in my own study, also based on the kinematics of global clusters, where I ignored the LMC. This is this data point here, and it lies a bit higher up. So this difference here is mainly caused by the inclusion of the LMC perturbation into the analysis, which, as was expected, could bias the result up by some 15–20%. And in doing these exercises, we could also measure the mass of the LMC, because again, the amount of perturbation is more or less linearly proportional to the mass of the LMC. So we can infer both the Milky Way potential and the LMC's mass. And again, different studies here, they converge more or less in the same ballpark. So to summarize this part, it seems that, well, the LMC is causing some damage to the galaxy, but we could also turn the table and use this damage to measure the mass of the LMC and constrain the distribution of mass in our galaxy, despite the perturbations that are caused by it. In fact, it's interesting that these studies could also not only infer the overall mass profile, but also try to place some constraints on the shape of the galactic halo at large scales, because streams are quite sensitive to it. And the trajectory of the stream on the sky would look different if the galaxy has a triaxial shape or it has a twisted halo. And that seems to be required by data. But interestingly enough, there isn't really a good agreement between different studies. So they all prefer non-spherical halos, but the direction of the orbital poles are not quite in agreement between studies. So it seems that we are still missing some important physical ingredients here, which might well be that in these studies, LMC was assumed to be moving just as a entire thing, but of course, in reality, it would be deformed. And the deformation obviously introduces some higher order complexity in this picture. Now, another topic that I wanted to highlight is that the past trajectory of the LMC is actually far from being certain. And in fact, it is very sensitive to the assumed Milky Way mass. Earlier this year, I was writing a review on this effect of the LMC on the Milky Way, including all these global deformations and perturbations to the stream and everything else. And one thing that I kind of summarized from all the previous studies was that LMC is just past its pericenter passage, likely for the first time, because that's what most people in this field tend to think, that it came from large distances beyond the virial radius of the Milky Way, and over the last several giga years, it was just approaching the Milky Way until it just passed the pericenter very, very recently. So now it's at 50 kiloparsec and started from like 500 or so. But these 3 lines here illustrate that by varying the mass of the Milky Way by only 10% from the baseline model, you could actually make the orbit much more short period. So the apocenter of that time goes back in time here. The apocenter of the orbit, you could shift it from 6 giga years ago to 3 giga years ago by changing the mass by only 10%. Or you can actually make it even more unbound if you make the galaxy lighter. And the reason for this high sensitivity is that LMC is very weakly bound, and currently it is sitting at the pericenter, so the kinetic energy and potential energy nearly compensate each other. Total energy is close to 0. So even if you change the potential energy by 10%, you change the total energy by a lot. And that means that the past orbit could be could look very different. So within the uncertainties on the Milky Way potential that we have here, which are of order 20% easily, give or take, all of these trajectories are possible. And in particular, these kind of trajectories, which had pericenter and apocenter, then another pericenter, they're also possible. So if you continue this exercise of orbit fitting further into the past, you'll find that trajectories could actually look like this. You come from large distance, you have one pericenter passage between 10 and 6, maybe 5 gigayears ago, then you go to apocenter, and then now you get another pericenter. So LMC might actually have second pericenter passage now. So that was a study informed by literature analysis, which then led to more in-depth analysis of these second passage trajectories. It took me about several weeks to complete the second paper, kind of crossing out the results of the first, not entirely, of course, but it's an alternative scenario. I think at this point, we cannot easily distinguish between these two possibilities because, as I said, it's mainly dependent on the mass of the Milky Way, and by itself, it's not very well known. So both first and second passage scenarios are quite possible given what we know about the data at present time, but eventually we should be able to distinguish them. And one interesting signature of the second passage scenario is the so-called the plane of satellites of the Milky Way. For context, the Milky Way has a few dozen of satellite galaxies, including the LMC, of course, including some of the galaxies that are orbiting the LMC, but also other galaxies that seem to be unrelated to LMC. And many of the satellite galaxies are located in a relatively thin plane, roughly perpendicular to the galactic disk. And not only in the plane, but also their velocity vectors, sorry, not the velocity, angular momentum vectors, also seem to point roughly in the same direction. So here is the sky plane where I'm showing not the positions of the galaxies, but directions of their angular momentum. And the LMC is sitting here, right in the center, in the blue region, and a bunch of galaxies that are also sitting close to it, maybe roughly half of the entire population of the galactic satellites shares this region, maybe a third or so. So they're sitting in the same orbital plane, they have similar orbital angular momenta. Could they have come to the LMC, or is it by chance? So this plane of satellites has long been a conundrum, and one possible explanation is that, in fact, it could have been caused by the LMC coming on the second pericenter passage, because if you look at the trajectories of some of the satellites, maybe if you can, yeah, try to show a movie. Yeah, so here is the movie. This is the Milky Way, this is the LMC, and a bunch of satellite galaxies that were originally part of the LMC. As you could see, we are now going through the first pericenter passage, and all of these guys, except for one, get stripped, and they now start orbiting the Milky Way. While LMC is doing its own business, it goes to the apocenter, now comes back to pericenter again, and the only thing that stayed faithful to it was the Small Magellanic Cloud, which is still a satellite of the LMC. But all other guys are still orbiting in the same orbital plane. So this kind of scenario is possible given that LMC comes for the second time instead of the first time. So if I were to plot these trajectories of some galaxies by possible trajectories, because of course nothing is very certain here, there is a lot of measurement uncertainties involved, a lot of uncertainties in gravitational potential and so on. But some of these galaxies might be coming from the same spatial region as the LMC, being initially gravitationally bound to it, shown here by the blue lines. Then at some point, after the LMC goes through this first pericenter passage, LMC continues on this trajectory. These galaxies get stripped and they keep orbiting the Milky Way on their own trajectories. But they're still were coming from the same cohort of galaxies as the LMC. Some of them, like the Small Magellanic Cloud, that stays close to the LMC at all times. Even now, it's only about 15 kiloparsec away from the LMC. So it's always was its satellite. Some galaxies like this one have roughly half, maybe less than half from chance that they were coming from the LMC system, but significant probability of staying close to the Milky Way at all times. So we cannot classify them with certainty. But all in all, quite a significant number of galaxies in this region, which share the orbital plane with LMC, might have come from the LMC system and being stripped on the first passage. Here is the illustration how it looks like. So the debris from the LMC are colored by the time of stripping, and the things that are still bound are here, still close to the LMC, and it has about between 9 and 11 galaxies that are currently bound to it, which are colored by blue, and then the galaxies colored red are all guys that possibly had been associated with LMC in the past, but had been stripped on the first passage, and that is some few gigayears ago. So this possibility is a kind of putting a bit more weight onto the second passage scenario, but of course it's not very conclusive, but it's one possibility. And another thing that I wanted to mention is that LMC also makes life difficult for people studying the kinematics of stars in the Milky Way disk. And that is because the Milky Way disk is warped, and that has been known, well, a long time ago. And the inner part of the disk is relatively flat, but if you go out, beyond the distance of about 15 kiloparsecs from the galactic center, it starts to be warped. And it is quite possible that this warp is caused by the LMC's perturbation, because as I said, the inner part of the galaxy is moving more or less coherently without being distorted. But the further out you go, the more significant becomes the perturbation from the LMC. So yeah, it is quite possible that the warp is created or at least contributed to by the LMC's passage. So far, it seems that it's not able to match it in detail, but there is also no reason why the warp would be created entirely by the LMC. There might be other contributing factors, like the passage of the Sagittarius galaxy, which is another perturber, or even the Milky Way's halo being deformed in some way. But at least it is a possibility. And in the future, as the LMC keeps orbiting the Milky Way, and of course it will be suffering from dynamic deflection even more and more, so eventually it will merge with the Milky Way a few gigayears in the future. And before it does so, it will introduce much more significant perturbation to the disk. So it will not destroy the disk, but it will certainly create much more significant kinematic deformations in the galactic disk, and will puff it up maybe by a factor of 2. And all the mass that LMC currently has in stars will be deposited somewhere in the outer part of the galaxy. So for context, the stellar halo of the Milky Way is believed to be about 10 to 9 solar masses, and the stellar mass of the LMC is about 3 times 10 to 9 solar masses. So when all this mass gets deposited in the halo, the galactic halo will increase by a factor of 4. And that is a significant thing. In fact, the halo of the Milky Way is unusually undermassive. If you look at galaxies like Andromeda or Centaurus A, one of the nearest spiral galaxies of comparable size, they have much more massive stellar halos. So that might well be because the LMC is just now coming in and starting to be stripped. And when the merger is complete, it will kind of bring our galaxy back to cosmic norm. And that's how I would conclude my talk, by looking at the future of the LMC. Of course, it will be destroyed, and for a good reason. But as our colleagues from University of Durham say, that this great collision between our galaxy and the LMC would actually restore the galaxy to normality in some way. And I would say that, yeah, we are all looking forward to restoring normality in the world, maybe in a time shorter than a few billion years from now. So thank you, and happy to take questions.
Thank you very much, Eugene. This was a very interesting talk and a very nice one. I hope our descendants will not see this catastrophe. Who knows? So let's see if there's any question from the audience. Please raise your hand. Let me ask you something that I didn't understood well. In the first part of your talk about the deflection angle from the streams of the stars, the model you are using to lower the deviations between the observations and theory, Do they use the mass of the LMC as a fitting parameter or not?
Yes, that's exactly how this works. You assume the potential of the Milky Way, and you assume a mass of the LMC, or the mass distribution of the LMC, and then, of course, it affects more or less linearly how much deflection you get.
And this is the best result you have for the mass of the LMC, or is there any better way to estimate the mass?
Well, that's one possible way. I wouldn't say that it's the best one, but it's certainly one that goes well with other complementary methods. I would say that two big classes of methods, one based on streams and the other based on the perturbation of the smooth halo and the kinematics of satellites and global clusters, they give comparable results, as I mentioned on this comparison here. The streams that are highlighted in blue and the method based on the kinematics of satellites kind of give similar answers. But importantly enough, I think we don't have to think about the mass of the LMC as being a single parameter. It's the whole mass distribution that is being probed by the streams, which probably makes it more powerful.
Okay, I understand. Thank you. Any other question? Maria? Okay, go
yes. Thank you, Eugene. This was a very, very nice talk, very interesting. And even though I'm not working in galactic dynamics, I think that I have learned a lot today. So, but I have a relatively naive question, because you described many different dynamical ways, perhaps, of potentially identifying a different passage, like a second passage of the LMC. So, is there any way also to use other methods that have to do with the chemical composition of the stellar populations, or how this would come into play into your modeling?
Yes, a very good question. Thank you. It's true that we should expect some sort of effect on stellar populations and on star formation history. And honestly, none of these models actually seem to give a definite match. From what we know from the observations is that LMC is actually actively forming stars right now. Perhaps a bit unusual among all satellite galaxies is the LMC and SMC are both very actively star forming. And the general expectation is that when you have a merger, or when a satellite galaxy crosses the virial radius of the host galaxy, the gaseous halo of the host galaxy introduces some sort of ramp pressure stripping, and the gas from the satellite will be partially or even fully stripped, and the star formation should cease. So for small satellites, that seems to be the case. The star formation histories of galaxies like Draco or Sculptor, they seem to be rather sharply peaked at early times. The bigger galaxies like Fornax and Sagittarius, they have extended star formation histories, and the LMC and SMC, they have star formation histories that are peaked around a couple of gigayears ago. So they don't seem to be tracing their orbits inside the Milky Way, but it might well be because the LMC and SMC are actually themselves quite large. So this ramp pressure stripping model might not apply to them, and they're much more tracing their internal evolution, because if this is a binary galaxy essentially coming as a single entity, both LMC and SMC orbiting each other and having much more effect on each other rather than being affected by the Milky Way. So I think in my impression is that at least you cannot ignore it, and it probably is the most dominant factor, the internal motion of this LMC-SMC pair that leaves imprints on the star formation history.
Okay, yes, thank you very much for the answer.
Another question? Yes, George?
Hey, thanks for the very nice talk and the interesting subject. I'm curious, motivated by the plot that you just showed, that there are calculations about for the Milky Way mass of 0.85 or 1.05. And I remember I saw something on the news recently that the Milky Way might be like 5 times lower mass than that, or something like 200 billion. Yeah.
Yeah.
So,
Okay. Let me. Yeah, that's a good question. Let me try to. Actually, I can show. Yeah, I can probably show it plots here. So this is the same plot on the upper side. This is the same plot I was illustrating here, which shows a compilation of dynamical mass measurements from various methods, extending from roughly 20 to more than 200 kiloparsecs. So these are mostly streams or global clusters or satellite galaxies, a little bit of stellar halo as well. These are, of course, not the only methods, and a number of works have been studying the kinematics of stars and dynamics of stars in the inner part of the galaxy, the solar neighborhood and beyond. And the circular velocity curve that you get from these experiments, many of them look like this. There is a general decline, and then there is a sharper decline here. Now, if you were to fit a galaxy mass profile through these curves here, you would really have to make it rather sharply truncated beyond the 25 or so kiloparsecs. And if you extrapolate it to infinity, you will get a mass that is indeed 5 times smaller. But here, if I were to compare this and this, there is basically no way they could agree. And at present, I think this seems to be one of the conundrums. There certainly is some systematic effect in either these kind of studies or these. I tend to think that this is most likely because, well, the errors here are large, but they might even be underestimated. And that's because of sheer difficulty to observe stars in the galactic disk at the distances well beyond the 20 kiloparsec. But yeah, it's also true that these regions of the disk are affected by the perturbations due to LMC and Sagittarius. So again, that might not play well with the assumptions going into the genes analysis. But I don't think there is a final word on it yet. But
Okay.
To summarize, I find it unlikely unless we do some weird changes to gravitational potential, or to the gravitational law, like, I don't know, making some modified Newtonian dynamics or something like this. It's unlikely that we can fit both the inner and outer parts simultaneously. So I don't know.
Okay, thanks very much.
Another question? Eugene, I noticed that your video, somewhat peculiar motion of the SMC, going like a zigzag.
Yes. So SMC will be orbiting the LMC. This is one possible realization. Of course, it's not the ultimate word, but yeah, it goes zigzagging around it. And at least we know if you reconstruct its orbit in the past for the last couple of 100 million years, the previous pericenter passage of the SMC around LMC was probably at a distance of only a few kiloparsecs. So it's a very close pericenter passage.
So it was a close encounter with the Milky Way that caused this?
No, I would say that these are all their internal struggles, right? So they both orbit the Milky Way roughly kind of as a binary system, but the orbit of the LMC SMC within LMC system, I don't think it is significantly perturbed by the Milky Way itself.
Okay.
Yeah. So it's clear that this interaction between two Magellanic clouds creates a lot of interesting features, like there is a Magellanic bridge that is a stream of stars that goes from one galaxy to the other. There are signs of perturbations in the outer part of the LMC. And while it would be tempting to ascribe those perturbations to the tidal harassment from the Milky Way, I think it's much more likely that this is actually perturbations caused by the SMC onto the LMC. And that's kind of connected but separate topic of study. And the fact that both are orbiting the Milky Way for the first or the second time probably plays a really little role in it.
Okay, thank you. Is there any other question? I'm not sure.
May I ask one more?
Yes, yes, Maria.
Yes, you didn't mention, I think, Eugene, about the dark matter profiles that you have been using in the simulations, or is anything new regarding this aspect that you found by looking at the interactions of the LMC with the Milky Way, or is it like you can reproduce the results by simply adjusting the gravitational potential coming from the baryonic matter, or you talk about the gravitational potential which is caused, or you try to adjust the gravitational potential which is coming from both baryonic and dark matter?
Yes, yes, it's the total potential that
it's a total one.
makes the difference. And in these models, I was more or less assuming standard cosmological things like Navarro-Frank White profiles for the halo. So far, there seems to be no indication that you cannot do it in the standard cosmology. Yeah.
Okay, thanks.
What is still puzzling, I was kind of hailing it as a way to explain the satellite planes, but I think it is true that these kind of satellite planes are still rather unusual. So it might well be that if you look at the large suite of simulations like illustrious or comparable cosmological simulations, you don't find many examples of Milky Way-like galaxies interacting with LMC-like galaxies and producing satellite planes like those we observe in our system. So it might be just we are lucky, but there are also indications of similar planes being around Andromeda and Centaurus, and that might still be a tension with the standard cosmological models. Well, the only thing that I'm saying here is that if given the observed properties of the satellites, their observed positions and orbits, it is quite plausible that they come from the LMC on the first being stripped on the first passage. But I cannot make any statement about how plausible is the overall situation here.
I see. Yes.
So it might still, I think it still remains quite a significant conundrum.
Okay. Yes. Thanks for the clarification.
Don't see any other hand raised. It's an opportunity that we have Eugene here to give answers to all of us.
Yeah, to settle all your doubts and the worries about the LMC and Milky Way in general, yes.
Not many people here are working on this. Okay, so let's thank our speaker again. Thank you very much, Eugene.
Thank you very much.
It was a very, very nice talk.
Yeah. I'm happy to.
We hope to see you in Athens sometime.
I hope so, yes.
Maybe in the next Gaia meeting.
Yeah, I think we are still doing progress, yes. All right, thank you.
Thank you very much. Bye.
Bye. Thank you very much.